Ready to explode with curiosity? In this video, we're throwing open the secret doors to the world of fireworks and firecrackers you never knew existed. Stick with us and you'll see how the magic of the brightest explosions is born from simple gunpowder. Discover the wild history of their creation and learn the unusual secrets of pyrotechnic masters. How do they create explosions in every color of the rainbow from ordinary black powder? Why can a single firework contain over 1,000 pellets, each burning its own unique color? What metals create red, green, and blue fire in the sky? And most importantly, why do masters remove even their wedding rings before work? And how can one stray spark destroy an entire lab? You'll find out how many hours it takes to create one professional firework, which countries produce 90% of the world's pyrotechnics, and what one epic New Year's Eve show costs. This story will make your heart race. Watch until the end, because the most important part is coming. Stay with us until the finale and you'll learn something that will flip your perspective. Don't miss it. Firecrackers. These are the more zippy guys in the pyrotechnic family. Their thing is sound, not spectacle. Even though they're simpler in design, they create the same magic, noise, and adrenaline. Like fireworks, the foundation of firecrackers is black powder, but here everything's a bit simpler. The main goal? Hit the right balance for a powerful bang without the extra special effects. Typically, a firecracker has a powder mixture, a casing, and a fuse. We'll talk about the filling later, but for now, let's learn a bit about the casing. It's a paper or cardboard cylinder that holds everything together. The material needs to be strong enough to contain the explosion until the moment of rupture, but not so strong that it creates dangerous shrapnel. The fuse is the most crucial element. It kicks off the explosive process. This could be a thin cotton cord soaked in chemicals, or more modern ignition mechanisms. The word firecracker comes from the French pétard, meaning explosion. Firecrackers, like fireworks, have Chinese roots. How do they make firecrackers? All components for the gunpowder mixture are carefully weighed and mixed to achieve the perfect consistency. Precision is critical here. Too much potassium nitrate and the explosion becomes uncontrollable. Too little and the firecracker won't ignite. Paper or cardboard tubes are cut to the required length, then filled with the gunpowder mixture. Typically, the casings have sealed ends to create the necessary pressure for detonation. At the top of the firecracker, they create a small opening where the fuse is inserted. It's secured using glue or special putty. The bottom and top edges of the firecracker are tightly sealed, usually with glue or heat sealing. This ensures safe storage and transportation. Next, firecrackers undergo rigorous testing. Manufacturers check sound levels, ignition speed, and blast quality. Not all firecrackers are created equal. Cheap firecrackers often have uneven filling, weak sound, and a higher risk of failure. They use lower quality materials like regular paper instead of cardboard. Quality firecracker casings are made from strong yet lightweight material. The gunpowder mixture is evenly distributed for a consistent effect. Fuses have precise burn times to give users enough time to move to a safe distance. Making firecrackers is no joke. Pyrotechnic factories have strict safety rules. Workers operate in small groups, wear anti-static clothing, and handle minimal amounts of mixture at any given time to reduce the risk of accidental explosions. Why are firecrackers so loud? This question often sparks curiosity. The thing is, a firecracker explosion isn't just a chemical reaction. It's the release of massive energy in a confined space. When gunpowder burns, it releases hot gases that rapidly expand, creating a powerful shockwave. And since a firecracker's casing is tightly packed, that wave is accompanied by the signature bang. Originally, firecrackers were used to scare off evil spirits, and only later did they become a popular form of entertainment. Making fireworks also requires mixing gunpowder with other components first. If gunpowder is the engine of the firework, then the other substances are the artists. They create the explosion of color, light, and shape. To create bright sparks, we need metal powders. That's aluminum, magnesium, titanium shavings. For vivid colors, they use metal salts like strontium, barium, copper, and sodium. Potassium nitrate, perchlorates, and charcoal amp up the explosive energy. After all, they're the oxidizers in fuel. And to hold all the components together, you need binding agents. Water-soluble glues, for example. Each component is first ground down into the finest powder. Imagine gleaming metallic particles dancing in the light as the craftsman preps them for mixing. The powders are so light, it's like they could just hang in the air like magic dust. The most important part begins when the ingredients go into the mill with ceramic or wooden balls. These balls rotate smoothly, grinding the mixture to perfect uniformity. The rustling and gentle tapping create their own rhythm, a sound that reminds you an explosion of colors is being born. When it comes to mixing ingredients by hand, traditional manufacturers approach the stage with reverence. Specialists carefully and slowly mix the ingredients with wooden or copper paddles. Why so slowly? Because even one accidental spark can trigger an explosion. The mixture looks like shimmering sand, where each component has its role. To prevent accidental explosions, the mixture is often moistened. Water doesn't just make the process safer, it adds mysterious alchemy as the gunpowder and dyes form tiny granules. The slightest mistake can lead to tragedy. You know what pyrotechnics masters do before starting work? They remove all metal objects, even rings, to avoid sparks. In many labs, cell phones are strictly banned, and clothing is chosen from anti-static materials. Even the air matters. Facilities maintain controlled humidity so the mixtures don't dry out and become explosive. Before packing the mix into a shell, craftsmen test how it burns. Flame bursts from a tiny sample and everyone in the room holds their breath. Will this be the perfect shade of blue? Are the sparks bright enough? It's like a dress rehearsal before the big show. Creating shapes and colors, that's the most exciting part of production. Want a heart or a star in the sky? It all depends on how the stars are arranged, those little pellets packed with special compounds. Where do those brilliant reds, greens, and blues come from? Chemical compounds. For instance, barium creates green, strontium gives you red, and copper produces blue. Once all the components are prepped, the next crucial step is loading the shell, where the heart of the firework comes to life. This is where the explosive mix and colorants transform into a finished product, ready to paint the night sky in every color of the rainbow. shell is the casing that holds all the fireworks components together. It's made from a special material capable of withstanding high pressure and temperature, yet light enough to soar into the sky. Cylindrical shapes are perfect for creating crisp patterns like rings, chrysanthemums, or peonies. Spherical shapes create symmetrical and three-dimensional effects, like a ball exploding with hundreds of sparks. The process of filling the shell is extremely important, because proper component placement ensures the desired effect. First, they take cylindrical or spherical blanks, usually made from cardboard, plastic, or special paper soaked in fire-resistant substances. The sphere typically consists of two hemispheres that are later joined together. It's crucial that the shell be perfectly airtight. This guarantees the burst happens at the right moment and with the right force. The gunpowder charge, as the main propellant, is positioned in the center of the shell. It's responsible for lifting the firework into the air and detonating it properly. Colorants and specialty mixtures are placed around the charge. Each star element is laid by hand or with specialized machines. Star elements are the pellets that burn in the sky. For spherical shells, these stars are arranged evenly to form a perfect sphere when detonated. In cylindrical shells, charges are often layered or shaped into specific patterns, depending on the intended effect. One standard spherical firework contains an average of 200 to 300 pellets. In large multi-layered shells, there can be over 1,000. To ensure the firework detonates at the right moment, a delay fuse is added to the shell, a small tube filled with a special compound that burns slower. The timer connects to the main charge, providing a delay between the rocket's launch and the explosion in the sky. After all elements are positioned, they're secured with a bonding compound or paper dividers. This is crucial so none of the components shift during launch. The casing is additionally wrapped with strong thread or glue to give it rigidity. Producing a single large professional firework can take up to 4 hours considering the manual assembly and inspection. For a large-scale show with several thousand shells, pyrotechnicians work for several months. The spherical shape is a classic in pyrotechnics. It ensures even distribution of stars during the burst, creating the effect of a perfect circle. Filling such a shell requires even greater skill. Each star is manually positioned around the central charge, and here everything depends on the master. How the components are arranged is how the burst will look. For example, to create a smiley face in the sky, the pellets are laid out in the shape of a face. When the gunpowder explodes, the pellets scatter precisely in the shape of the intended pattern. Every year, the world produces over 200,000 tons of fireworks. The production leader is China. It accounts for roughly 90% of global output. For major holidays such as US Independence Day or New Year's in Sydney, up to 10,000 individual fireworks are launched in a single night. This can last over 20 minutes, and the cost of a single show sometimes reaches $5 million. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would grind to a halt, lights would go dark, and rocket engines would fall silent. And here's the thing, it's so rare that the entire world is competing for every single gram. Tungsten has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. That's a temperature at which most other metals would have long since turned to vapor. Annual global tungsten production ranges from 85 to 100,000 tons per year. But here's what's striking. Up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number showing just how valuable it is. Total global tungsten reserves are estimated at roughly 3 to 3.5 million tons, nowhere near the reserves of iron or aluminum. But here's what really matters. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that will flip your understanding of the metal-holding civilization together. Picture a massive underground mine somewhere in Vietnam, China, Russia, or Canada, the world's biggest tungsten producers. Deep in the Earth's belly, hundreds of feet down, lie ores containing tungsten. Not pure metal, but complex minerals, wolframite and scheelite. Wolframite is a compound of iron, manganese, and tungsten. Scheelite is calcium tungstate. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep underground. It's tough, dangerous work, requiring high-tech equipment and strict safety standards. Thousands of tons of ore get hauled to the surface daily by massive underground trucks. Powerful blasts shatter the rock, exposing the valuable ore. It's like a controlled earthquake in miniature. After the blast, the ore gets loaded into haul trucks with capacities up to 300 tons and transported to the processing plant. After extraction, the ore goes to a processing plant. Here it undergoes several stages to separate valuable wolframite or scheelite from other rocks. First, the ore is crushed in crushers and mills into a fine powder. Massive jaw crushers with deafening roars break down car-sized chunks into fist-sized pieces. Then the crushed ore enters ball mills, giant rotating drums filled with steel balls. In these mills, the ore is ground into an extremely fine powder, almost like flour. Next, various enrichment methods are applied, such as gravity separation, magnetic separation, and flotation. Gravity separation uses the difference in density. Tungsten minerals are heavier than waste rock. Magnetic separation separates weakly magnetic wolframite particles from non-magnetic impurities. Flotation is a process where the ground or powder is mixed with water and special chemical reagents in large tanks. These reagents selectively attach to tungsten mineral particles, making them water repellent. Air is then pumped through the mixture, creating millions of tiny bubbles. The tungsten mineral particles latch onto these bubbles and rise to the surface, forming a foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The resulting concentrate is then processed at metallurgical plants to obtain pure tungsten. This is a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent calcination to produce tungsten oxide. The concentrate is dissolved in alkaline solutions at high temperatures. Ammonium paratungstate, an intermediate compound, is then precipitated from the solution. This compound is calcined at temperatures around 1100 to 1500 degrees Fahrenheit, producing tungsten oxide, a yellow powder. Tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. Inside specialized furnaces, tungsten oxide is heated in a stream of hydrogen. The hydrogen strips away oxygen from the tungsten oxide, releasing pure metallic tungsten. The result is a fine gray tungsten powder, the foundation for every product that follows. It's from this powder that tungsten rods, bars, and other blanks are formed through sintering. The tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, forming a dense, durable material. Sintering temperatures can reach 5,400 degrees Fahrenheit. At that temperature, the powder particles begin to fuse, creating a monolithic structure. The process takes place in furnaces with controlled atmospheres to prevent oxidation. One of the most critical applications is the production of hard alloys known as tungsten carbides. These alloys, combining tungsten with carbon, plus cobalt or nickel as a binding agent, rank among the hardest man-made materials. Tungsten carbide is created by heating tungsten powder with carbon at temperatures around 2,500 to 2,900 degrees Fahrenheit. Tungsten carbide crystals form, which are then ground into powder. This powder is mixed with cobalt or nickel, serving as a binder, pressed into molds, and sintered. Tungsten carbides are used to manufacture cutting tools, drill bits, milling cutters, lathe tools that can machine the hardest metals and alloys. Without tungsten carbides, modern mechanical engineering, metalworking, and oil and gas extraction would be impossible. 2 pounds of tungsten can become a drill bit capable of boring thousands of feet through rock, demonstrating its incredible efficiency. Tungsten is also widely used in the military industry for manufacturing armor-piercing shells and bullet cores. Thanks to its high density and hardness, tungsten alloys have excellent penetration characteristics, providing high effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is irreplaceable. It's used to produce filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components requiring high heat resistance and electrical conductivity. Because of its high melting point, it's used in the space industry for components subjected to extreme temperatures. High-temperature alloys containing tungsten are used in aircraft engines, turbines, and other devices operating under conditions of extreme heat. Alloying with tungsten increases the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with lower toxicity. Plus, tungsten is used to create ballasts and counterweights in race cars, aircraft, and yachts thanks to its high density. It's also a component in certain jewelry pieces because of its hardness and scratch resistance. Tungsten is one of the least abundant elements in Earth's crust, which makes its mining and production especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential but not yet explored resources, the total volume could be significantly higher. This is, of course, incomparably less than reserves of metals like iron or aluminum, which underscores its strategic value. Annual global tungsten production, measured in tons of pure metal or tungsten oxide equivalent, fluctuates, but in recent years it's been approximately 85 to 100,000 metric tons per year. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine being able to take a worn-out tool that's already served its purpose and turn it back into something new, without spending energy and resources mining ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is among the most advanced and efficient of all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, demonstrating its value and economic viability. Where does used tungsten come from? The main source of secondary tungsten material is, of course, spent cemented carbides. Those cutting tools, drill bits, and milling cutters made from tungsten carbide. After intensive use, they wear down, lose their edge, or break. Instead of tossing them in a landfill, they're collected and sent to recycling plants. Other sources include tungsten-containing scrap metal, leftovers from tungsten product manufacturing, plus certain electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of ore mining and initial processing. Recycling dramatically reduces tungsten production's environmental footprint. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production greener and more responsible. And so, after a journey from underground blast through grinding into powder, and through flotation with millions of bubbles, through chemical dissolution and reduction in a hydrogen atmosphere at 1800 degrees, through sintering at 3000 degrees, a metal is born with the highest melting point on Earth, capable of withstanding 6192 degrees Fahrenheit, a metal without which modern industry, aviation, aerospace, and medicine would be impossible. And the most remarkable part, nearly half of this metal is born anew from old tools, making tungsten one of the most environmentally friendly strategic materials of our civilization. What if I told you there's a metal that's 15 times rarer on Earth than gold? And to mine just 1 ounce of it, you need to process 10 tons of ore. A metal whose entire annual supply would fit in an ordinary room, while all the gold in the world would fill 3 Olympic-sized swimming pools? Every year, the world produces only 180 tons of platinum. That's 17 times less than gold. South Africa produces 120 tons. 74% of global production. Russia's in second place with 23 tons. To extract 1 ounce of platinum requires processing 10 tons of ore, while for gold, just 2 to 3 tons. The Merensky Reef, Upper Group 2, and Platreef contain only 2 to 10 grams of platinum per ton of ore. After flotation, the concentrate is heated to 1500 degrees Celsius to burn off iron and sulfur impurities. Then they use aqua regia, a mixture of nitric and hydrochloric acids, to dissolve the platinum. The concentration of platinum in Earth's crust is only 0.5 parts per million. Stick around till the end. You'll discover a secret that even jewelers won't tell you. Picture an underground mine several miles deep somewhere in South Africa, in the Bushveld province, home to the world's largest platinum deposits. These aren't open-pit mines. They're narrow tunnels blasted through rock up to 2 miles beneath the surface. Here, platinum is extracted from thin layers, reefs, that stretch for hundreds of miles but measure just 6 inches to 5 feet thick. 3 main reefs: the Merensky Reef, Upper Group 2, and Platreef. The Merensky Reef, discovered by Hans Merensky in 1924, has historically dominated global platinum production. Here, platinum reaches its highest concentration, 50 to 60% platinum group metals. Upper Group 2, a chromite-rich reef, more stable but with lower gold, copper, and nickel content. Platreef, a wider reef with lower platinum grades but higher base metal content, roughly 5 times more. Miners drill holes into the reef walls and pack them with explosives. After detonation, the shattered rock containing platinum and other metals is transported to the surface for processing. The ore gets crushed, then goes through flotation. That's a process that separates minerals based on how they stick to air bubbles and water. Mills grind the ore down until 60% of the particles pass through 75 micrometers. Then the ground ore gets mixed with water, and collector reagents are added, things like xanthates and dithiophosphates, which make the sulfide minerals containing platinum hydrophobic. Water repelling. Air gets pumped through the mixture, creating millions of tiny bubbles. The hydrophobic particles containing platinum stick to the bubbles and rise to the surface, forming a froth that gets skimmed off. Hydrophilic waste rock particles stay at the bottom. Platinum in Merensky ores is closely tied to base metal sulfide minerals, copper, nickel, and cobalt. The platinum group metals are present either as discrete platinum group minerals included in or attached to the sulfides, or in solid solution with the sulfides. The base metal sulfide minerals in Merensky: pyrrhotite, pentlandite, chalcopyrite, and traces of pyrite. After flotation, the concentrate still contains less than 1% platinum. Now, the concentrate heads to the smelter. It's dried and then heated in electric furnaces to temperatures exceeding 2,700 degrees Fahrenheit. Air is blown through the molten metal to oxidize iron and sulfur impurities. Sulfur oxidizes to sulfur dioxide and gets removed as exhaust gas. Iron oxide is removed as phyllite slag. Platinum's melting temperatures are significantly higher than other metals due to the presence of chromium, which makes them incompatible and requires special furnace design. The power capacity of platinum smelting furnaces reaches 19.5 megavolt amperes and 68 megavolt amperes. Energy consumption runs 800 to 850 kilowatt hours per ton of concentrate. Platinum's high melting point means impurities like iron burn off, and the result is a powdery sludge of platinum group metals: rhodium, iridium, ruthenium, and osmium, plus platinum itself. The converter's slag phase contains significant amounts of trapped platinum metals and gets recycled back to the smelting furnace to recover those captured metals. The converter mat gets cooled down, crushed, and processed at a base metals refinery. Here, hydrometallurgical processes dissolve the copper and nickel, leaving behind a residue rich in platinum group metals. This platinum metals residue heads to a precious metals refinery, where various solvent extraction and precipitation methods separate out the individual metals. Getting pure platinum requires further refining. Typically, this involves aqua regia, a mix of nitric and hydrochloric acids in a 1:3 ratio. Aqua regia is one of the few acids that can dissolve platinum. When the concentrate is treated with aqua regia, the acid produces chlorine, which bonds with the platinum, forming chloroplatinic acid. The final step uses ammonium chloride to convert the chloroplatinic acid into ammonium hexachloroplatinate, which can be calcined to yield pure metallic platinum. Platinum content in the residue after hydrometallurgical processing can reach 5,900 ounces per ton. That's an enrichment of nearly 500 times compared to the original flotation concentrate. Now, a bit of history. In 1735, Antonio de Ulloa and Jorge Juan y Santacilia witnessed indigenous Americans mining platinum while the Spanish traveled through Colombia and Peru for 8 years. Ulloa and Juan found mines with whitish metallic nuggets and brought them back home to Spain. Antonio de Ulloa returned to Spain and established the first mineralogical laboratory in Spain, and was the first to systematically study platinum, which happened in 1748. In 1783, French chemist François Chaboneau was the first to obtain a pure sample of platinum metal. In 1801, English scientist William Wollaston invented a method for efficiently extracting the metal from ore. Growing demand for the metal led to the discovery of major deposits in the Ural Mountains in 1824 and in Canada in 1888. This ultimately led to geologist Hans Merensky's discovery of the largest platinum deposit on Earth in 1924. Platinum is primarily used in automotive catalytic converters. In 2014, out of 218 tons of platinum sold, 98 tons, 45%, went to vehicle emission control devices. 74.7 tons, 34%, to jewelry. 20 tons, 9.2%, to chemical production and petroleum refining. 5.85 tons, 2.7%, to electrical applications like hard disk drives. The remaining 28.9 tons went to various other minor applications, such as medicine and biomedicine, glass-making equipment, investments, electrodes, anti-cancer drugs, oxygen sensors, spark plugs, and turbine engines. The most common use of platinum is as a catalyst in chemical reactions, often in the form of platinum black. It's been used as a catalyst since the early 19th century, when platinum powder was used to catalyze the ignition of hydrogen. In automotive catalytic converters, it completes the combustion of low concentrations of unburned hydrocarbons from exhaust gases into carbon dioxide and water vapor. Platinum is extremely rare on Earth, occurring at a concentration of just 0.05% in the Earth's crust. Platinum often occurs chemically unbonded as native platinum and primarily as an alloy with other platinum group metals. Most commonly, native platinum is found in secondary deposits among alluvial sediments. The alluvial deposits used by pre-Columbian peoples in the Chaco Department, Colombia, are still a source of platinum group metals today. Another major alluvial deposit is located in the Ural Mountains, Russia, and it's still being mined. When comparing the rarest precious metals by annual mine production, platinum is far rarer than gold. We're talking about more than 15 times rarer by annual output. In 2018, silver, gold, and platinum mine production totaled 860 million ounces, 108 million ounces, and 6 million ounces respectively. Producing a single ounce of platinum requires about 10 tons of ore. For comparison, gold needs around 2 to 3 tons of ore to produce 1 ounce, while silver takes 5 to 10 tons per ounce. Global demand for platinum in 2023 was estimated at 7.5 million ounces. The world's largest platinum producer, Anglo American Platinum, produced 1.75 million ounces of platinum in 2023. Russian company Norilsk Nickel produced 593,000 ounces of platinum in 2022. Every year, an additional 2 million ounces, 60 tons of platinum, comes primarily from recycling auto catalysts and jewelry. What makes platinum stand out is just how difficult it is to extract. Platinum mining is extremely labor-intensive. The KEL process represents a potentially significant improvement in platinum concentrate processing technology from an economic standpoint through dramatically reduced energy costs. Compared to matte smelting, electricity consumption drops by 82%, and overall carbon dioxide emissions decrease by 70%. And so, having traveled from a thin reef deep underground in South Africa, through blasting, crushing, flotation with millions of bubbles, through smelting at 1500 degrees Celsius, through dissolution in aqua regia, through precipitation with ammonium chloride and calcination, platinum is born. A metal 15 times rarer on Earth than gold, requiring 10 tons of ore to be processed for a single ounce, whose entire annual supply, just 180 tons, would fit in a single room. A metal that catalyzes chemical reactions, cleans the exhaust of millions of cars, and adorns fingers with jewelry that never corrodes.